Hi, we're happy to present Beyond RGB, Scene Property Synthesize with Neural Radiance Field. Here are Mingtong Zhang and Shuhong Zheng from UIUC. This is a joint work with Zhipeng Bao, Michelle Hilbert, and Yuxiong Wang. Comprehensive scene understanding is important for real-world applications such as semantic segmentation, object detection, surface normal estimation, and so on. A general method is to develop data-driven discriminative models for scene understanding. Here, we propose a novel perspective to learn expressive 3D representation by synthesizing various scene properties. To achieve this, the important first step is to render photorealistic images. One of the most influential works for novel view synthesis is Neural Radiance Fields, known as NERF. Given a set of images captured from multiple views, NERF learns to render the scene from novel observing views. NERF shows great capability of implicit geometry-aware 3D representation. Here, we are interested in a different question. Could this implicit representation be extended to richer scene property beyond RGB? The answer is yes. We developed a NERF-style model that is able to render not only photorealistic images, but also various accurate scene properties. By sharing knowledge among these synthesized tasks, our framework better bridges generative learning and discriminative learning. Our model takes the 5D vector as input and learns a mapping to various scene properties. Specifically, we adopt a shared positional encoding network to build future embeddings for the 3D spatial locations. The encoder shares knowledge through the implicit representation across different properties. Since some properties are not sensitive to the view direction, we adopt two types of decoding networks. The view-dependent branch takes additional 2D view input, together with the encoded 3D locations to synthesize scene properties, while the view-independent branch predicts the scene properties with encoded 3D locations only.
We conduct our experiments on two commonly used datasets, replica and blended MVS. 5 representative scene properties are chosen, which are semantic labels, surface normal, shading, key point, and edge. We first show a video of our rendered results with all the 5 scene properties and RGB images. Our SS-NERF produces good rendering of RGB along with other scene properties when the view direction changes. We compare our model with 2 baselines. The heuristic baseline predicts scene properties by projection from the closest view. The hybrid baseline first uses NERF to render RGB images for novel views, and then use a discriminative model to obtain predictions for the rendered images. The chart shows that our SS-NERF model consistently outperforms the baselines on all 5 tasks. Here's a visualization. It further demonstrates the good performance of our SS-NERF over the hybrid baseline, which performs RGB generation and scene property prediction separately. We observe that our SS-NERF, which jointly predicts RGB images and vision tasks, can benefit from the shared representation, which encodes 3D geometry information. Next, we explore the relationships of our chosen tasks via transfer learning. In our experiments, knowledge transfer from A to B means we first train our model on task A with full supervision, then fine-tune it on task B with only sparse supervision. The chart shows the transfer learning results. From the highlighted parts, it reveals that some tasks are more related than others. For example, surface normal and semantic labels are more closely related, so as edge and key point. Finally, there's an interesting application where SS-NERF can serve as an auto-labeler. When we use a pre-trained discriminative model to label the images, the predictions would have flaws. To solve this problem, we train an SS-NERF model using the RGB images and the flawed annotations. With the RGB information, the SS-NERF model can correct these inconsistencies during optimization. making the labels more accurate. More results and analysis are discussed in our paper. Welcome to check for details. Thanks for listening.